The critical infrastructure is the industrial base on which the competitiveness and security of a nation are dependent. The current state of a nation's critical infrastructure may be at risk. The internet has become the central nervous system of a nation, both public and private. A nation's critical infrastructure continues to be vulnerable to natural disasters and cascading cybersecurity attacks. It is in the context of software engineering methods and technology, CMAT, and its essence kernel, framed by Ivor Jacobson, that the user story on critical infrastructure resilience is being demonstrated. The overall demonstration of the mission to achieve critical infrastructure resilience is being initiated in three parts: the composition of a user story and the subject of today's presentation, the preparation of a software systems architecture, also the subject of today's presentation, and the project plan in terms of principles and foundations in the way of working. While the critical infrastructure being framed is influenced by thinking in the United States, nations around the world share many of the common challenges discussed and may find the approaches and prescription useful. Following a summary opening, I will discuss the challenges of the critical infrastructure with particular focus on the banking and finance sector cascade and propagation risk, a maturity framework for assuring resiliency under stress, the model-based software systems architecture that frames the solution, and a glimpse at next steps. The critical infrastructure protection model is insufficient. In addition to CIP, a critical infrastructure resilience model needs to be adopted. We need to move from static lock and chain protection beyond the combination lock to the strategy of a chessboard with moving parts capable of anticipating, avoiding, minimizing, withstanding, and recovering from the effects of threats and vulnerabilities. We need to shift the locus of control for the nation's cybersecurity from protection to resilience. One respected researcher seemed to concede the high ground of resiliency, that is, avoidance, in associating resilience with the Timex slogan, "Take a licking and keep on ticking." The question then becomes, what perimeter is being secured? In protecting a network node or a physical facility in a geographic region, each node or facility is to be protected and made survivable. In achieving resilience, propagation and cascading effects across the network and region must also be curtailed. This is made difficult by the context and culture challenges of the industry sectors within the critical infrastructure. The capabilities needed to impact cross-cutting issues cannot be expected to evolve in a loosely coupled environment. They must be holistically specified, architected, designed, implemented, and tested if they are to operate with resilience under stress. A management, process, and engineering maturity framework is necessary to advance the assurance of software security, business continuity, system survivability, and system of systems resiliency capabilities. Resiliency is the ability to anticipate, avoid, withstand, minimize, and recover from the effects of adversity, whether natural or man-made, under all circumstances of use. Resiliency applied to a system of systems focuses on cross-cutting issues. Cross-cutting effects stem from dependent relationships. Some dependent relationships are planned and intended interactions between industry sectors, such as financial transactions embedded in telecommunications, electrical, transportation, and medical operations. Other dependent relationships are indirect and stem from outsourced commoditized services that bring with it opportunities for common single-point failures among industry sectors, such as the internet, the cloud, the global positioning system, and common vendors. The critical infrastructure is composed of the numerous industry sectors that do the heavy lifting. Some key sectors are listed here. Utilities and energy contain power generation and distribution systems, nuclear power control systems, and energy resource allocation systems. Telecommunications contain network control and switching systems, satellite control and management systems, and mobile communication systems and protocols. Banking and finance contain electronic commerce and electronic funds transfer systems, transaction processing systems, security and privacy management systems, and network management systems. Transportation contains route management and collision avoidance systems, avionics systems, air traffic control systems, navigation and position location systems, and embedded automobile control systems. Medical systems contain medical device control systems, patient record systems, and insurance and payment systems. The operations within the industry sectors of the critical infrastructure are diverse and complex. These industry sectors comprise an accidental system of systems that intersect operationally without a plan and design in advance. Each sector system was constructed within its own context and culture. In operation, these sector systems may inadvertently impose their own context and culture on others and clash with uncertain and unintended operational results. Industry sector practice varies widely in their domain engineering approaches, resulting in diversity in architecture, models, and patterns, including their representation. Formality within an architectural framework facilitates the imposition of distributed supervisory control, interoperability, and operation sensing and monitoring protocols. Industry sector maturity in management and engineering processes varies widely, resulting in diversity in configuration management, frequency of release, conformance to requirements, and traceability among lifecycle artifacts. Strong code management practices facilitate reconfiguration and reconstitution. Industry sector practice varies widely in fielding and operating practices, resulting in diversity and accountability and control, supply chain management, civility and pushback, and willingness to expend off-the-clock effort. Exercising strong control over the workforce facilitates business continuity and survivability. Industry sector impacts from government regulation vary with respect to export control, tax policy, intellectual property, privacy, and antitrust litigation. Exercising strong government control facilitates compliance for the benefit of the commons at the expense of initiative for the self-interest. Industry sector public expectation and confidence vary with respect to trust, loyalty, and satisfaction. The financial and medical sectors depend on public trust. The electrical and telecommunications sectors depend on customer loyalty and satisfaction. If the critical infrastructure is to be resilient, its sector managers and systems must respond to guidance from intelligent middlemen whose influence is felt before, during, and after a crisis. Intelligent middlemen possess the broad range of hard and soft skills spanning the cultural, ethical, legal, business, process, management, and engineering dimensions needed to meet the challenges of the critical infrastructure in anticipating, avoiding, minimizing, withstanding, and recovering from cross-cutting effects and to impede the emergence of propagating and cascading effects. The intelligent middlemen are positioned at the center of things and serve as the traffic cop for identifying and driving resolution of cross-cutting issues. From this vantage point, the intelligent middlemen are able to obtain superior situation awareness. For example, they ensure that recovery time objectives are coordinated, interoperability protocols are followed, distributed supervisory control functions are coordinated, and operation sensing and monitoring functions are applied. The banking and finance sector illustrates the stovepipe culture, environment, and technological vulnerabilities that stand ready to trigger societal impact. Its institutional dependence on public trust and its operational dependence on electrical and telecom resilience under stress, with its tightly coordinated recovery time objectives, make it vulnerable. In banking and finance, the financial services industry depends on a network of systems that process instruments of monetary value in the form of deposits, loans, funds transfer, savings, and other financial transactions. The network is composed of banks, other depository institutions, and the Federal Reserve System, as well as underwriters, brokerages, and mutual funds. In addition, there are industry utilities, including the New York Stock Exchange, the Automated Clearinghouse, Depository Trust Clearinghouse Corporation, and the Society for Worldwide Interbank Financial Telecommunications, as well as underlying third-party electronic processing services. Clearing and settlement systems are the most critical business operations at risk for financial markets, and the disruptions of clearing and settlement processes would have on an immediate systemic effect on critical financial markets. The use of the term systemic risk is based on the international definition of systemic risk in payments and settlement systems. The Federal Reserve Board specified that the following functions are critical to the operation and liquidity of banks and stability of financial markets and require same-day recovery. Large value interbank funds transfer, securities transfer, or payment-related services such as Fedwire, Clearinghouse Interbank Payment System, Depository Trust Clearinghouse Corporation, and the Society for Worldwide Interbank Financial Telecommunications, automated clearinghouse operators, key clearing and settlement utilities, Treasury automated auction and processing system, large dollar participants of these systems and utilities. The banking sector depends on maintaining the trust of the banking community and the banking public. In large measure, this trust is maintained through the transparency and verification inherent in exchanges. Without this trust, the banking system itself risks anarchy. Under what circumstances might the trust in the banking system be tested and stressed? At the close of each business day, it is the expectation and practice of the banking community that the banking ledgers of branch offices be reconciled and balanced to the penny, and that securities and trading firms create a daily profit and loss statement. Under what circumstances of use might the banking ledgers be thrown out of balance, impacting the daily closing and settlement process, and the next day opening? More specifically, what is the least cybersecurity exploit capable of impacting next day closing? Overall, the stock exchanges and their associated clearinghouses have performed due diligence and taken the steps necessary to ensure the resilience of their operations. The maturity framework for assuring resiliency under stress delivers value through management process and engineering capabilities and solutions that address security, continuity, survivability, and resiliency. The system perimeter focus areas include commitment to a business case, security and depth, business continuity, and survivability. The essential focus areas needed to extend this perimeter to the system of systems context needed to demonstrate resiliency include coordinated recovery time objectives, interoperable information and data exchange, operation sensing and monitoring, distributed supervisory control, and information and data recovery. To achieve maturity in the assurance of resiliency under stress, The enterprise must satisfy the goal-based argument at each level. The objective of the maturity framework for assuring resiliency is to drive the business case and enterprise commitment towards the assurance of software security, business continuity, system survivability, and system of systems resiliency. Level 1 is a state of affairs where there is inability to advance and exhibiting evidence of apathy, denial, management inaction, and lack of engineering know-how. The Level 2 goal is to demonstrate commitment to security assurance through strategic management, internal processes, and defense in depth. How is commitment achieved, quantified, and expressed? Commitment is achieved by coping with the stresses and conflicts between competitiveness and security. Commitment is quantified by calculating security return on investment in terms of preparation and incident costs, cleanup costs, lost opportunity costs, and reconstitution costs. Commitment is expressed through a Chief Security Officer leadership program and security assurance operations. The Level 3 goal is to demonstrate business continuity assurance through compliance management, external processes, and product engineering. How is business continuity achieved? Business continuity begins by focusing on supply chain management, including global sourcing and open source. It extends to regulatory compliance and aspect oversight and assessment. Business continuity culminates in the systematic crisis management steps of prevention and response that sustain stability or result in a return to stability. The Level 4 goal is to demonstrate the achievement of system survivability through the management of faults and failures, sustainability processes, and reliability, maintainability, and availability engineering. Central to system survivability is resistance and recognition of cyber attack or cyber threat and the recovery and reconstitution of enterprise operations following. The Level 5 goal is to demonstrate the achievement of systems resiliency through the management of external interactions and dependencies, the control of distributed supervisory processes, and the practice of next-generation software engineering. A defined engineering challenge of adopting resilience throughout the nation's critical infrastructure is needed. The recovery time objectives among industry sectors must be coordinated. Interoperability of information sharing and platform operations must be assured. Distributed supervisory control protocols must be in place. Operation sensing and monitoring must be embedded. And digital situation awareness must be enabled. The systems of systems architecture and engineering operational concept underlying resiliency under stress is shown here. Interoperability, operation sensing and monitoring, and coordinated recovery time objectives form the foundation for digital situation awareness. Intelligent middlemen, response tactics, the identification of cascade triggers, and information and data recovery tactics form the ingredients for distributed supervisory control. A nation's critical infrastructure is composed of systems. Resilience in the critical infrastructure can be reasoned about using the systems coupling diagram framed by Harold Budd Lawson. The model is composed of a situation system, an interacting respondent system, and systems assets, instantiated for use as services as needed by the respondent system in its interaction with the situation system. The systems coupling diagram is a template and pattern for software systems architecture of all kinds. A resilient software system architecture based on the systems coupling diagram would be capable of delivering a resilient critical infrastructure system of systems. In accordance with the systems coupling diagram, The software systems architecture for critical infrastructure resilience calls for the following allocation of control, functions, and persistent data and assets. The situation system is populated with the man-made critical infrastructure sectors and the intelligent middleman control node. The respondent system is populated with the Level 5 System of Systems Resiliency Engineering mission focus areas intended to interact with the situation system and its intelligent middlemen in anticipating, avoiding, withstanding, mitigating, and recovering from the effects of adversity under all circumstances of use. The system assets is populated with the level 2 through 4 facilities focus areas and their services to be instantiated by the respondent system in its interaction with the situation system and its critical infrastructure sectors. More specifically, the critical infrastructure situation system is composed of utilities and energy, banking and finance, medical systems, transportation, and telecommunications, as well as public health, food and agriculture, federal agency, regional response, emergency response, and intelligent middleman control node. Each sector of the situation system is composed of the control, functions, and persistent data and assets local to the sector. The respondent system is engineered as a system of systems architecture composed of coordinated recovery time objectives, interoperable information and data exchange, operations sensing and monitoring, digital situation awareness, distributed supervisory control, and information and data recovery. The situation system is composed of the control, functions, and persistent data and assets of the global system of systems. The system assets include services and facilities to be instantiated by sector, including enterprise security commitment management services, enterprise business continuity services, and system survivability engineering services. The system assets is composed of the facilities and service assets made available to situation system and its sectors by the respondent system. In accordance with the systems coupling diagram, the software systems architecture for critical infrastructure resilience calls for the allocation of control, functions, persistent data, and assets. The architecture rules of construction associated with each factor are shown in the figure. As mentioned earlier, the overall demonstration of the mission to achieve critical infrastructure resilience is being initiated in 3 parts: the composition of a user story, which is the subject of today's presentation, the preparation of a software systems architecture, and the project plan in terms of principles and foundations in the way of working. The state of this demonstration for requirements, software systems architecture, way of working, and others are shown here, with the current state of progress in italics type and next steps shown underlined. Stakeholder has been recognized. That is the critical infrastructure sectors. It now needs to be represented by individuals pursuing this vision. Opportunity has been identified, and clearly software is needed. A value proposition needs to be established that will rally the stakeholders to see it to a conclusion. The requirements have been conceived, they've been bounded, they are coherent. It remains to review that with the stakeholders in the context of the value proposition to ascertain that they are acceptable. The software system has an architecture selected, and that architecture needs to be demonstrable as the next step. The team needs to be selected going forward. The way of working principles have been established, foundations have been established, and we now need to put all of that in use and press forward in the form of a project. The work has been identified, but it remains to be initiated. The work product has been identified, and it needs to be initiated so we can move forward. This concludes the presentation of the user story with respect to the critical infrastructure resilience. Here is my contact information. I would be happy to receive questions and have discussions with people on this important subject.